Hello, 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 everybody. We're looking at the 2000 Euclid paper put out by the University of Waterloo. And we're up to question number 5. So if you're looking for the other questions, you can go back and see previous videos. We've done questions 1, 2, 3, and 4. And now we're on number 5. It's a two-part question. And we have an A part, which, as we might expect, is a light bulb. In the diagram, AD equals DC, denoted by these two dashed lines in the middle. Okay. If sine DBC is 0.6, so that's 6/10 or 3/5, and ACB is 90 degrees, that's a right angle, what is the value of tan ABC? Okay. Well, as always, let's get to drawing a picture so we can better understand the situation and we can mark it up with whatever notation we need. Okay, draw our own copy of the picture. We have A, B, C, and we have a point D halfway between the two. Okay, so we know we have a right angle here, and we know a little bit of information about this angle right here. So let's let theta equal angle DBC. Right? Was it DBC? Yes, DBC. Okay. So we know that sine of theta is 0.6. And we're asked for a tangent. Now, when I see a question that gives me an explicit sine and then asks for an explicit tangent, and I'm not given any of the side lengths, and I'm not really given any other angles to go on, what I usually try and do is I think back to what I learned in grade 10. I don't know where the curriculum is at now, but Sohcahtoa is the abbreviation that's used. If you're looking at a right angle triangle and you're looking at one of the non-right angles, call it theta, then the sine of theta is the same as the length of the side that's opposite of theta divided by the hypotenuse. The cosine, so C-A-H, the cosine of that angle theta is the adjacent side length. So one of these side lengths is not the hypotenuse and is still touching that theta. Then that adjacent side length divided by the hypotenuse is the same as the cosine. And Sohcahtoa, the tangent of theta, and we're looking for a tangent in this question, is the opposite side length divided by the adjacent side length. Okay, so that immediately springs to mind with this question right here. We're presented with a very nice sine 0.6. Okay, and we can quickly rewrite sine of 0.6 as something like 3/5, and we're asked for a tangent. Okay, so that's what we're looking for here. So my mind immediately springs to, okay, if I want a tangent of this angle right here, while there are other ways to compute this sort of stuff, for example, using this theta, we could grab our calculators and actually figure out what theta is, and what this angle is, and what this angle is. But I think the much simpler way of doing things is to say, okay, we have a sine here, and that tells us something about this opposite, so DC, and once we know something about DC, we know something about DA, and it also tells us a little something about the hypotenuse. Okay? So, I think we want angle ABC here. I'll just double check that as well. Yeah, we want tan ABC. Okay. So, for those of you who haven't seen it or need it recalled, Sohcahtoa, opposite adjacent hypotenuse. Sine theta is opposite over hypotenuse. Cos theta is adjacent over hypotenuse. And tan theta equals opposite over adjacent. So the tangent that we're looking for is tan ABC. Well, that's going to be the opposite, so AC, over BC. Okay? So we're looking for what's the length AC, what's the length BC, or more importantly, what's the ratio between them. And we don't know a whole lot about them, but one thing we are given is that sine, we know that the sine of theta is 3 over 5, but sine is opposite over hypotenuse. So opposite, that's CD, over BD is 3 over 5. So all we know is that BD and CD are in a ratio of 5 to 3. So let's call this 5x and 3x. That way, although we don't know the actual length CD, we definitely have the ratios correct, and that's what's important here. This question is all about ratios of this triangle, so we'll never figure out what CD is. In fact, there's no way to. You could scale this triangle up or down. It's not going to change the tangent of ABC, as long as we have these proportions. Right away, we can see AC is twice DC. So that's 2 times 3x, or 6x. So right now, we have the top side of our tangent. All that's left is to figure out BC. Triangle BCD is right. So by the Pythagorean theorem, BD squared is BC squared plus CD squared. And so if we substitute in, now we still don't have actual values, but we do have 5x. 5x squared is BC squared. BC is the other side that we need for our tangent, plus CD squared, which is 3x squared. Okay, we'll continue this on the next side. So if we expand that out, 25x squared is equal to BC squared plus 9x squared. And if we rearrange that, we get that 16x squared is BC squared. So BC is 4x. And that gives us everything we need to figure out this ratio. Remember, we need AC, which we figured out is 6x, over BC. So 6x over BC, which we just figured out is 4x. And we get a final answer of 3/2, and that's our tangent. Okay? So that rather beautifully gives us the tangent, and all we had to do was remember the Sohcahtoa rule, the ratios, when you're dealing with a right-angled triangle. Only right-angled triangles permit this rule. That made things a little easier. Okay, how about 5b? Written style question. On a cross-sectional diagram of the Earth, the x and y axes are placed so that the origin is the center of Earth, and point C at 640,000 is the location of Cape Canaveral. Okay? A space shuttle is forced to land on an island at point A which is it. 543 and 3.39. Each unit represents 1,000 kilometers. Okay? So really this point here, we're saying it's 6,000 kilometers from the center of the Earth. 6,400, I guess. Determine the distance from Cape Canaveral, point C, to the island as measured along the surface of the Earth to the nearest 10 kilometers. So right away, nearest 10 kilometers, that suggests to me that we're probably not dealing with very nice fractions, very nice angles, very nice cosines and sines. And so we're going to have to grab ourselves a calculator and be very careful about the steps that we take to make sure we don't introduce too many rounding errors. Because we need to round to the nearest 10. So it'll end in, maybe it's 480. Maybe we get the final answer and it says 476.327 or something like that. We would round it to the nearest 80 and we need to be, the nearest 10, and we need to be very careful that we don't introduce too many errors in our calculations and round to the wrong number. Okay? So what can we do? Well, we're asked to determine a distance along the surface of what I can only assume they're approximating as a circle. Okay? This isn't a geology or a astrophysics class, so we're not actually concerned with the fact that the Earth isn't a perfect sphere. So this here is a circle, and so we're looking for measuring distance on a circle. So we're looking at how do you calculate arc length. Okay. First, we're going to draw ourselves a copy of the picture, as we almost always do. Someday I'll get better at drawing circles, I swear. You know what I should do? I should really just sort of keep a circle with me that I can draw on. I do have a pencil holder, I just don't know if it'll be the right size. No, it's not working. This experiment has failed. We're just going to freehand draw a circle. I'll look into that in the future, though. Whatever, it's as good as we're going to get right now. Okay, so origin, C, and A up here, and that was at, I think, 5.43, 3.39, and we had 6.40, and 0, I'm not going to write the 0.00 in. Alright, let's just double check. Okay, we got our numbers correct. So what we want is, we use purple, we want this distance here, A to C, to the nearest 10. So this is what's called an arc length of the circle. Alright, what we have is a certain pie slice cut out, and it all depends entirely on this angle here, angle angle AOC. And from that, we can actually determine what the arc length is in terms of the radius. So for a circle of radius R, the arc length associated to theta degrees is found by the formula. Okay, once we have this theta, we have to assume whether or not theta is in degrees or radians. That does change our formula ever so slightly. So I think I'm going to use degrees in this question. No reason not to. Most calculators default to degrees. So we know what the actual total length around the circle is. That's the circumference. and that's 2 pi r. But we're not going all the way around the circle, no. We're going a certain fraction around the circle, theta. Now, theta's got to feature somewhere in our formula. We're going theta out of the total 360 degrees, so that gives us the fraction. Theta degrees out of 360 degrees, that is the fraction of the circumference that our arc length gives us. Okay? Well, I would say it's clear that 6.40 is the radius. Okay? I wouldn't say that that's particularly difficult to see. C goes, it's only got coordinates in the x-axis, and our origin was at 0, 0. So it's not that hard to see 6.4. That's going to be the radius. So we've got the radius. Pi is a constant, 2 is a constant, 360 degrees is a constant. So all we need to do is find theta. So how are we going to find theta? Well, there are probably a couple ways, but the first one that comes to mind is we have this point A up here, and it reminds me of our circle definitions for what cosine and sine and tangent are. And so what we can do is we can form this right angle triangle here, and we have this length theta here. And suddenly we have a right angle triangle, and the height is going to be the radius, 6.4, times the sine of theta. And the length here, up until this point, is going to be, we'll call this point B, is going to be the radius, 6.4, times the cosine of theta. Okay? But however you look at it, we do have a right angle triangle with a known height and a known base, and we can use that to figure out what theta is going to be. So you can pick any one you want. If you want to use So or Ka out of our Sohcahtoa, that's fine. You will need to calculate the hypotenuse, which is going to be 6.4 because it is the radius of the circle. But using the Toa, we know that tangent theta is going to be opposite over adjacent, and that's 3.39 over 5.43. So let's work out what that is. 3.39 divided by 5.43. Okay, so I don't get a particularly nice fraction in my notes, or on my calculator, I guess. $339 divided by 3. So I'm getting something like 113 over 118. That is not a nice number. Oh, sorry, 181. And I don't think we can simplify that anymore. I think 113 is prime. Yes, it is prime. Okay. And this is about 0.62 according to my calculator. Okay, 0.6243 is what I've got. Am I going to use this in the calculations? Absolutely not. When I use my calculations, I'm going to use the whole fraction, 113 over 181. If you start rounding off your numbers now, you can introduce a source of error that can definitely put you off by more than 10 kilometers, in which case you're going to get the wrong answer in the end. Okay? So you got to keep that in mind. Anytime we're doing this calculation, and we're about to do one on our calculator, we're going to do the inverse tan or the arctan. We're going to do the arctan of 113 over 181. not the arctan of 0.6243, even though that's what I have written out here in our notes. This is just a little approximation so we can see what numbers we're working with. Okay? So, theta, which is the number we highly desire, is tan inverse. Some people write it arctan. I usually switch back and forth between the two of them. So we're going to use tan inverse 113 divided by 181. And I'm getting about 31.976 degrees. Am I going to use that? No. I'm going to keep it on my calculator as the 31.97692.033. I'm going to be as accurate as I possibly can until the end. Okay? Now that I have my theta, I can use that formula. I can use the formula for computing the arc length because we know the radius and now we know theta. So the arc length AC, well, that's theta divided by 360 times 2 pi r. So that's about this number over 360 degrees, 2 pi 6.4. Okay? So, I take my calculator. It's still got that long string, and I immediately divide it by 360. That way I know I have as accurate a fraction of the total circumference for my arc length as possible. Multiply it by 2, and we multiply it by pi. Some calculators have a nice nifty pi button, and 6.4, and I come out with 3.5718, and just going to keep going on like that. 56284. That's what I've got sitting here on my calculator. So that's the distance, but we have to reread the question because each unit represents 1,000 kilometers, and we want the distance to the nearest 10 kilometers. One unit equals 1,000 kilometers. So we multiply by 1,000, so we move the decimal point over to the right by 3 places. And we round to the nearest 10 kilometers. That's 3570. Okay? And that should be our final answer. And of course, I should have kilometers in there. And of course, if you have a different answer, by all means, leave it in the comment. Perhaps I have Perhaps I have made a mistake. If you ever think that I might have made a mistake, by all means, go to the CEMC website. You'll find a link in the description, and you can look at their solutions and see how they did things. Because I'll admit it, I'm not perfect, and I do make the occasional mistake. Maybe I make more than an occasional mistake. I'll leave that up to you guys to judge. But you can always just go see their solutions as well. Okay? But that does it for question number 5. We've got questions 6, 7, 8, 9, and 10 left to go. You can already see 8, 9, and 10 there, just a pure written question. And 6 and 7 follow the familiar pattern we've seen for a little while. Light bulb question and written question. So we're going to take a look at question 6 in the next video, and I will see you guys then.